For decades, science has told us a pretty clear, kind of terrifying story about at the heart of our galaxy, 26,000 light years away, a monster is lurking in the dark. It's a gravitational titan, 4 million times heavier than our sun, gobbling up anything that gets too close. We call it Sagittarius A. We have even taken its picture. It's, for all we know, a scientific fact. The supermassive black hole at the center of Milky Way. But the story of science is really a story of overthrown ideas. Every fact we think we know is only as good as its ability to stand up to new questions and new ideas. And today, we're going to explore one of those challenges. We are going to do a little thought experiment based on real physics that asks a wild question. What if that monster in the middle of our galaxy isn't a black hole? What if a totally new theory could explain everything we see, from the way stars dance around it to that famous fairy picture, but with something else, something maybe even more mysterious? To really get the scale of this challenge, you have to respect the reigning champion. The case for Sagittarius A isn't just strong, it's the result of a lifetime work of hundreds of scientists and even earned a Nobel Prize. The story starts not with a picture, but with something nobody else could see. Back in the 1990s, astronomers like Andrea Ghez and Reinhard Genzel pointed their powerful telescope at the galactic center and just saw chaos. Stars were moving at absolute ridiculous speeds. They focused on one star, S2. For years, they tracked its journey, watching it whip around a completely empty spot in space. At its fastest, S2 was moving at about 2.5% the speed of light. To make a star move that fast, you need crazy amount of gravity packed into a tiny space. By tracing S2's complete orbit, scientists used basic laws of physics from Kepler to Newton to weigh this invisible object. The number they got was staggering, about 4 million times the mass of our sun. 4 million suns, all crammed into space smaller than Mercury's orbit. In the known universe, there is only one thing that can be that massive and that compact. Yes, a black hole. This evidence was so good that Ghez and Genzel won the 2020 Nobel Prize in Physics for their discovery. For most of us, that was it. Case closed. Then, in 2022, we got what felt like the final proof, the smoking gun. The Event Horizon Telescope, which is basically a network of radio telescopes that act like one giant Earth-sized dish, released the first ever direct picture of Sagittarius A. And there it was, a fuzzy, glowing donut of super hot gas, ringing a perfect circle of darkness. That dark spot in the middle, the shadow, was exactly what theories predicted. It was a silhouette of the event horizon itself, the point of no return. The evidence seemed overwhelming. Sagittarius A was our black hole. But science is never really settled. Its greatest strength is that it's always willing to question everything. So let's start our thought experiment. Let's imagine that a wild new study pops up in big science journal. It's written by a team of physicists, let's call them Valencia Crespi and Carlos Arguelles. Their paper doesn't just question the black hole idea. It offers a complete, radical alternative that they claim fits all the facts. They propose that the object at the center of our galaxy isn't a black hole, but a super dense core made of pure dark matter. Now, that sounds like something out of sci-fi movie. So let's break it down. We know that about 85% of all the stuff in the universe is dark matter. It's the invisible scaffolding that galaxies are built on. We can't see it or touch it, but we do see what its gravity does all over the place. Our hypothetical study suggests that dark matter is made of particles called fermions. In physics, you're either a fermion or a boson. Fermions are basically the introverts of particle world. They have a hard rule against being in the same state in the same place at same time. It's called Pauli's exclusion principle, and it's the reason atoms don't just collapse on themselves. This refusal to be squished together creates a powerful outward push called quantum degeneracy pressure. It's the same pressure that holds up dead stars like war dwarfs and neutron stars against their own crushing gravity. Our imaginary scientists would argue that a certain kind of dark matter, fermion, could do the same thing at the galactic center. Trillions of these particles could fall inward, getting squeezed until their collective quantum pressure pushes back and stops the collapse. The result isn't an infinitely dense singularity, but a stable, unbelievably dense ball of dark matter. An object with a mass of 4 million suns, but without the one thing that makes black hole a black hole. No event horizon. A dark matter heart instead of a black hole in space-time. This is where the thought experiment really gets fun. A new theory is one thing, but can it actually explain all the evidence we have for Sagittarius A? According to our hypothetical scientists, the answer is yes. First, what about the orbits of those S stars? The path of a star like S2 really only depends on how much mass is in the middle and how it's spread out. A black hole model puts all 4 million solar masses into one tiny point. Our dark matter core, while not a point, would be so compact that from a star's perspective, the gravity would feel identical. The math works, the orbit fits just as well with dense ball of dark matter as they do with a black hole. Round 1 is a draw. Okay, but what about that picture, that famous donut from Event Horizon Telescope? That shadow is everything, isn't it? This is where our imaginary researcher Valencia Crespi would offer a pretty stunning answer. She might say our dark matter model also creates a shadow that looks just like the picture. How's that possible? It all comes down to extreme gravity. You don't actually need event horizon to make a shadow. Any object that's massive and compact enough will bend space-time so much that it messes with light. Simulations run by this hypothetical team would show that their dark matter core, even though it has a surface you could technically stand on, warps space-time so much that it creates a lensing effect. It creates a patch of darkness in the middle, and the hot gas around it would still form a bright, swirling ring. The end result? A picture that, with the telescopes we have now, looks almost exactly like the image that we have of Sagittarius A. It's a gravitational imposter, another draw. But here's where the dark matter model might have an edge. There is a little nagging issue with the standard black hole model, sometimes called the scale problem. A black hole is one object, and a giant spread out halo of dark matter that whole galaxy sits in is another. They are treated as a separate thing. But when astronomers use data from missions like Gaia to map stars way out in the galactic suburbs, their speeds don't perfectly match what you would expect from a central black hole plus the standard halo. Our dark matter core model connects these two things beautifully. It suggests the super dense core and a giant halo aren't separate at all. As our other imaginary scientist Carlos Arguelles might put it, we think the central object and the halo are just two parts of same continuous substance. The dark matter is just the densest at the very center and gets more spread out farther you go. This singular continuous blob of matter could potentially explain the speeds of stars both near and far away, solving both mysteries in one elegant idea. For the first time, the challenger seems to have a real advantage. Let's just pause here and think about what it would mean if this were true. The consequences aren't just big, they would change everything. For one, we would have to rewrite the first chapter of every modern astronomy textbook. The idea that huge galaxies are built around supermassive black holes is a pillar of cosmology. If the heart of our own galaxy isn't a black hole, you have to ask, how many others aren't? Are these dark matter cores a normal thing and black hole at the center an exception? The whole story of how galaxies grow would be up for debate. Second, it would be the biggest breakthrough in the history of particle physics. After a century of looking, we would finally have figured out what a dark matter is. If the galactic center is a stable ball of fermions, it would tell us about their mass and how they behave. We wouldn't have found a particle in the lab on Earth, we would have found a giant celestial object made of them. The hunt for the dark matter would be over. And finally, we would have to re-examine all the most extreme objects in the universe. We have detected gravitational waves from merging black holes, and we have seen shadows of Sagittarius A and the monster in galaxy M87. Are all of them really black holes, or could some of them be dark matter cores without an event horizon? The universe might be a far stranger place than we thought, filled not just with singularities, but with these giant quantum objects hiding in plain sight. This is where our thought experiment comes back to reality. A good scientific theory has to be testable. It has to make a unique prediction that lets us tell it apart from the competition. And in the battle of a black hole and a dark matter core, there is one. It all comes down to the very edge of the shadow. According to Einstein's theory of general relativity, a true black hole's event horizon should create something very specific, a thin, sharp, brilliant circle of light right at the edge of the shadow, called as the photon ring. This ring is made of light rays that have been captured into orbit, circling the black hole maybe once or twice before escaping towards us. It's the fingerprint of an event horizon. Our dark matter core wouldn't have this because it has no event horizon. Light can't get trapped in a stable orbit around it in the same way. Its shadow would have slightly fuzzier, less defined edge. So, the ultimate test is simple. Find the photon ring. If we can see the sharp ring of light, it's a black hole. End of story. If, with better and better images, we find that the ring isn't there and the shadow's edge is softer than predicted, then the challenger wins. And this isn't science fiction. Right now, astronomers are working on the next generation Event Horizon telescope to make its images sharper. At the same time, other instruments are being upgraded to track stars and gas flares even closer to the center. They are literally hunting for the tiny clues, the photon ring, that could only be explained by an event horizon. We will likely have the answer within the next decade. So, could the center of a Milky Way not be a black hole? Right now, scientific consensus is clear. Sagittarius A, the 4 million solar mass black hole, is still the reigning champ. It's the simplest and best explanation for all evidence we have. But this thought experiment shows us that there are real, physically possible alternatives waiting in the wings. It shows us the most beautiful part of science. Nothing is sacred. Even our most beloved ideas have to be tested over and over again. The possibility that the heart of our galaxy could be a gigantic object made of the universe's most mysterious stuff is a powerful reminder that we should always be ready to have our minds blown. Whether the final answer is a black hole or a dark matter heart, the search itself is a journey worth taking. The truth is out there, written in the dance of stars and the bending of light, and we are getting closer to reading it every single day. Thanks for watching.